In part 1, we build the whole machine. Given a system you steer and a cost you want small, you form the Hamiltonian. Then you write three conditions: the state equation, the co-state equation, and one more, the rule that pins down the control. That last rule was this: 0 equals the partial of h with respect to u. Set the slope of the Hamiltonian in the control direction to 0, sit at a flat spot, and you're optimal. But that rule is fragile. Setting the derivative to 0 only makes sense if the control is free to move in any direction. If you can nudge it a little either way and watch the Hamiltonian respond. And in the real world, controls are bounded. A thruster only pushes so hard. A steering wheel only turns so far. Write that as the absolute value of each control component is at most 1. There's a wall and the best move might be to slam right into it. If the optimal control is pressed against its limit, the slope of h is not 0 there. And yet you can't do any better because you're not allowed to step past the wall. So the flat spot rule breaks. The whole question of this video is just this: what replaces 0 equals the partial of h with respect to u when the control is clamped? Forget control for a moment. Here's the same puzzle in its simplest possible form: minimizing an ordinary function on a closed interval. Picture a curve, and you may only stand somewhere between the two end walls. If the lowest point sits somewhere in the middle, an interior minimum, then the curve is flat there. The derivative is 0. Step a little left, you go up. Step a little right, you go up. That's the familiar rule: d minus f equals 0. But now suppose the lowest allowed point sits right on the wall, at the very edge of the interval. The curve there might still be tilted, sloping downhill, wanting to keep going. The derivative is not 0, and yet you're stuck, because going further means leaving the interval. So the condition weakens. All you can say is that every step you're actually allowed to take leads uphill, or stays level. D minus f is greater than or equal to 0. You can't improve even though the slope isn't flat. That one weakening from equals 0 to greater than or equal to 0 is the entire idea of this video in miniature. Here it is, the heart of the whole subject: Pontryagins minimum principle. It says the optimal control is the one that makes the Hamiltonian as small as it can possibly be. Written out: h evaluated at the optimal state, the optimal control, the optimal co-state, and time is less than or equal to h evaluated at that same state and co-state, but with any other admissible control you could have chosen instead. And this holds for every admissible control u in the allowed set, at every single instant between the start and the final time. Look at what changed. In part 1, we asked for a flat spot, the derivative of h in the control direction equal to 0. Now we ask for something stronger and more honest. Not a flat spot, but the actual global minimum of the Hamiltonian over the entire set of controls you're allowed to use. At each moment, look across every legal control and pick the one that drives h lowest. That's it. That's the principle. The optimal control minimizes the Hamiltonian. Let's put the complete set of necessary conditions side by side. 3 lines. First, the state equation: x dot star equals the partial of h with respect to p. Second, the co-state equation: p dot star equals minus the partial of h with respect to x. Those two are exactly what we had in part 1. The state moves with the gradient in p. The co-state moves with minus the gradient in x. Nothing about them changed. The third line is the only thing that's new. Instead of setting a derivative to 0, we now demand h at the optimal control is less than or equal to h at any other admissible control, the minimum condition. And here's the reassuring part. If the optimal control happens to land in the interior, comfortably inside its limits, not touching any wall, then minimizing a smooth function inside its domain means the derivative is 0 there, and the old rule comes right back. 0 equals the partial of h with respect to u. Pontryagin principle doesn't throw away part 1, it contains it. The flat spot rule was just the special case where the minimum sat in the open. The key word now is global, the true minimum of h, not merely a place where it's level. Let's watch it bite on a concrete problem. A little second order system. x1 dot equals x2 and x2 dot equals minus x2 plus the control u. The cost is 1/2 the integral of x1 squared plus u squared. Keep the state near 0 while spending little control. If the control were free, part 1 would hand us the answer instantly. U star equals minus p2, the unconstrained optimum. But now clamp it. The control must stay between -1 and +1. So we minimize the Hamiltonian over that box. As a function of u, the Hamiltonian is just an upward parabola whose lowest point sits at minus p2. If minus p2 falls inside the interval from -1 to 1, great. Sit right there, the unconstrained answer survives. But if minus p2 wants to be bigger than 1, the parabola is still heading down at the wall. So the best legal choice is to jam against the wall at +1. And if it wants to be below -1, you jam against -1. The result is the saturation law. Use minus p2 when it fits and clip it to plus or -1 when it doesn't. The unconstrained answer clipped at the walls. Now a different kind of goal entirely. Forget penalizing the control. This time, the only thing we care about is getting there fast. The cost is the elapsed time itself. J equals the integral of dt, which is simply the final time minus the start time. Minimize the clock. Go as fast as physically possible. For this class of problem, the system has a special shape. It's control affine. That means x dot equals a of x and t plus a matrix B of x and t times the control u. The control enters linearly. No u squared, no funny business. Just b times u added on. Form the Hamiltonian. The running cost for a minimum time problem is just 1. Every second costs 1 second. So h equals 1 plus p transpose times the quantity a plus b u. And notice where the control lives. Only inside that linear term, p transpose bu. The Hamiltonian is a straight line in u. Hold on to that. It's about to decide everything. The Hamiltonian is linear in the control. So ask yourself, how do you minimize a straight line over a box? You don't sit in the middle. A tilted line has no flat spot inside. You go all the way to a corner, to whichever extreme the slope points. And the slope is the coefficient of u in the Hamiltonian, p transpose times b. We give that quantity a name and a color, the switching function in amber. When the switching function is positive, the Hamiltonian increases as you raise u. So to minimize, you slam u to its lowest value. When it's negative, you slam u to its highest value. Put together, that's the bang bang law. U star equals minus the sign of b transpose p. So there is never an in-between. The optimal minimum time control is always pinned to a limit. Maximum effort all the time. Full thrust one way or full thrust the other. The only thing the switching function decides is which way. That's why it's called bang bang. Let's make it completely concrete with the cleanest example there is, the double integrator. Think of a cart on a frictionless track. x1 is its position, x2 is its velocity, and the control u is the force you push with. Bounded, the absolute value of u at most 1. The dynamics, x1 dot equals x2 and x2 dot equals u. The Hamiltonian is 1 plus p1 times x2 plus p2 times u. The control appears only in that last term. So the bang-bang law says u star equals minus the sign of p2. The whole control is decided by the sign of one costate. Now watch the costate. Its equations give p1 dot equals 0. So p1 is just a constant. And p2 dot equals minus p1, a constant slope. That means p2 is a straight line in time, minus c1 times t plus c2. And a straight line crosses 0 at most once. So its sign flips at most once, which means the control switches at most one time over the entire maneuver. Full thrust one way, one flip, full thrust the other. That's the whole optimal trajectory. But when do you flip? For that, leave the clock behind and draw the phase plane. Position x1 across the bottom, velocity x2 up the side. Every full thrust trajectory traces a parabola. There's a family curving one way under +1 and a family curving the other way under -1. Stitch them together and a single beautiful curve appears, the switching curve. x1 equals -1/2 x2 times the absolute value of x2. It's an S line through the origin. Define the switching function of the state as S of x equals x1 plus 1/2 x2 times the absolute value of x2. The feedback law is then dead simple. Above the curve, where S is positive, push -1. Below it, where S is negative, push +1. So the optimal maneuver is slam to a limit, ride a parabola until you hit the switching curve, flip exactly once, then slide along the curve straight into the origin. And the general theorem says it stays this tidy. For a system with real eigenvalues, the control switches at most n-1 times. A trader knows this shape. Bang bang is the strategy that refuses to hedge halfway. It flips between fully aggressive and fully passive. And the switching curve is the line in state space that says which one you're in right now. Change the cost one last time. Instead of minimizing time, minimize fuel. J equals the integral of the absolute value of u, not u squared, the absolute value. You pay for thrust in proportion to how much you use, and crucially, coasting at 0 is completely free. That free coasting creates a brand new shape of answer. Outside a certain band, you fire full thrust against the sign of the state, just like before. But inside the band, the cheapest thing to do is nothing at all. Shut the engine off and drift. So the law has 3 settings: full one way, off, full the other way. People call it bang off bang, with a dead zone in the middle where you coast for free. This is the contrast that ties the whole chapter together. Minimizing fuel, the integral of the absolute value of u, gives you on-off control, hard switches with a dead zone. Minimizing energy, the integral of u squared, gave you continuous, smoothly saturating control, like the clipped line from earlier. The shape of the cost decides the shape of the controller. And on a desk, that dead zone is exactly the no trade band around your target inventory. Small imbalances, you do nothing. Only past the edge do you act. One honest caveat before we close. Everything in the Bang Bang story leaned on the switching function being non-zero. Its sign told you which corner to slam into. But what if it isn't just 0 at an instant, but stays exactly 0 over a whole stretch of time? Write it. P transpose B is identically 0 on some interval from T1 to T2. Then the coefficient of the control in the Hamiltonian vanishes. The Hamiltonian stops depending on U altogether, and the minimum principle, asked which control is best, simply shrugs. Every value gives the same Hamiltonian, so it can't choose. The principle goes silent. We call that a singular interval. It's a genuine subtlety, and resolving it takes higher order conditions beyond the minimum principle itself. We'll just name it and respect it, a real frontier of the theory, not a flaw in what we've built. So here is the complete map. When the optimal control sits in the interior, free to move, you set the derivative to 0. 0 equals the partial of h with respect to u, exactly part 1. When the control is bounded and the optimum is pressed against a limit, you replace that with the real rule. U star is the control among all admissible ones that minimizes the Hamiltonian, and the shape of the cost picks the shape of the answer. Bang bang, full effort with sharp switches for minimum time. A dead zone, coast then fire for minimum fuel. Step all the way back and look at the trilogy. We started in the calculus of variations, learning to make a whole path optimal. That gave us the Hamiltonian and the necessary conditions in part 1. When the system was linear and the cost quadratic, the co-state became a matrix times the state, and out fell clean feedback through the Riccati equation in part 2. And when the control was bounded, the flat spot rule gave way to Pontryagins minimum principle, here in part 3. Through all of it, one object did the work. The optimal control was always the one that made the Hamiltonian smallest. That was the key from the very first frame. That's the trilogy.